All right, everyone, welcome back. We're going to do our second session with Sasha. So we've updated a couple things on how we're doing the remote session. We've switched from the Blackboard to writing on a tablet, which we're hoping will be more visible. We're trying to make it easier for students to ask questions. We have the microphone volume louder in the room. And so we're going to pass around the mics. I have one, Willie has one. If you have a question, raise your hand. We'll bring you a mic. Sasha says, just interrupt him. And we've tested this volume and hopefully they'll be able to hear you asking your question all day. Any questions about the questions? All right, if not, let's turn it over to Sasha for lecture number 2. Sasha.
Thank you, Oliver. And as you suggested, it might be more effective that way. And I thought that's because you haven't seen my handwriting. But I learned today that apparently students learn better from bad handwriting because they have to constantly actively engage in understanding. I don't know if it's true, but let's try. So let me start with a short recap of what we discussed yesterday. We set as a goal for these lectures to construct something which looked like non-perturbative amplitude in 4 dimensions. And then we start to get some inspiration how we actually can solve this problem. We start considering perturbation theory, and we just took as a seed these 4 points, and then we iterated, and we saw that in fact, yes, it looks like the whole perturbation theory. We can think of this in the Bootstrap terms as a dispersive iterations of unitarity, and there are many graphs which you can obtain by this basic gluing operation where you glue along the 2-particle cut, like here, etc. But then at three loops, we encountered these graphs where you can see that
Sorry, can I interrupt really quickly?
Sure.
So the claim about the 2-particle gluing, something that I was confused about yesterday, but it came up again now, I guess, is that the eye diagram on the second row on the far left has 4-particle cuts as well. So does that not also come from multi-particle gluing or no?
No, exactly. You see, so how do you glue that? You take this diagram, say, and you just glue it to this. So if I cut it here, I can construct it by 2-particle gluing of the diagrams which I obtained in the first row. So
But
what I'm saying, yeah. So
no, sorry, go on.
Yeah, so I'm not saying that you cannot find the cut, which is a 4-particle cut, which is this. But what I'm saying is that all these diagrams you can get by iteratively gluing through a 2-particle cut. For example, if you glue this diagram to this diagram, so you take these 2 legs and you connect them here, this is exactly what you get. Whereas if you try to do this with this guy, you see it's just there is no cut, which is a 2-particle cut, all 4 particles. So in this way, that if you start iterating unitarity and you just stay in this sector, you will not get this diagram. And all these diagrams, by the way, let me also notice. So first you update. So they, if you wish, 2pi reducible, and they're all planar. I don't know if it answered your questions.
Yeah, that makes sense. Maybe actually just a follow-up question about the diagram on the left on the bottom. Could that not be seen as coming from a 2-particle cut, but where you have corrections to the external legs?
Yeah, so external legs are not corrected here because, you know, we are doing think of this as some non-perturbative problem where you're scattering physical particles of mass m, which are on shell.
Yeah, that makes sense. Thank you.
Now, you see that here that, okay, if you have this 2-particle gluing operation, you take the object we are studying, and this is a 2-to-2 scattering amplitude on the left and on the right. And so this is something which, if you wish, if you're hoping to solve it, that's fine. But then when we go to multi-particle gluing, you see that we have this new object T2 to 4. And we will have, at this point already, you can ask me or yourself, how are we going to ever solve this problem? Because the system of equations is not closed, of course. And so this is the crux of the problem, and we will have to answer this question somehow. But we see that these objects naturally arise, they're all connected, and we will have to do something about it. But let's not worry about this yet and just try to learn some lessons and get some inspiration. And so the second inspiration, which I told you, is that if you look at all these diagrams, you can write them in this suggestive form where you have these integrals, and these integrals allows you to immediately tell what is the complex properties of these functions of two variables s and t. And say if you take discontinuity, meaning say, and yeah, someone asked me, what does it, I use this word maximal analyticity, what does it mean actually? So this is very clear from here. If you look where all the non-analyticities of these functions in the product of two complex planes for s and t, you see they are all given by these cuts, which are dictated by unitarity. S equal 4, t equal 4, and u equal 4. And these cuts, you cannot get rid of them. They will be there just because you produce particles in all channels. So this will be surely there, but there is nothing more at this point, and that's why it's called maximal. You cannot get more than that. This analyticity will be there, and this representation is called Mandelstam representation, and I called it, so here in this slide I have dispersive iterations, where dispersive means that we express the amplitude in terms of this our starting point, which was lambda, and its discontinuities, which is called single spectral density, and this is a double spectral density. And that's how you can effectively compute all these diagrams. You just iterate dispersion relations and unitarity. So here one point is that there is, as you see, there is a symmetry under STU. And in fact, yes, this symmetry requires that this spectral density is symmetric. And this ST and U, these are the crossing symmetric point that I used. Now, this is, I called it non-perturbative lesson, but it's really a guess. It's an inspiration. People tried to prove it in the 60s. They couldn't, but they also couldn't disprove it. It's an open problem.
Regarding that, I have a question.
Yeah.
Does this include non-perturbative effects like instantons?
In principle, yes, it's a non-perturbative formula. So here, the basic equations that underlines, of course, if you ask me, well, do we have four-dimensional models with instantons where this formula has been checked? No. But in principle, this picture behind analyticity based on this unitarity, which is non-perturbative notion. So the amplitude itself acquires all kinds of corrections from instantons for whatever non-perturbative physics you have. But this equation should be okay with that. There is no problem. So, yeah. Now, there is also when I talk about unitarity, well, this is one picture how you can think about it with diagrams, but it's also useful to decompose in what's called partial waves. So this is simply, problem is invariant under rotation, so it's useful to decompose on this basis. And then unitarity is a statement when you scatter in this J partial wave, the probability to scatter is less or equal than 1. And then here there is a difference between gravity and something like QCD, is that if you say scatter pions, there is this range where you do not have enough energy to produce 4 pions, and so the probability 2 to 2 must be 1. Whereas when you say S larger than 16, you can produce maybe 4 pions, or then it doesn't have to be 1, but it has to be less or equal than 1 to 2 to 2. So this is called sometimes elastic and inelastic unitarity. And notice that there is slight, this will be also perhaps recurring topics, there is a slight tension. I started this formula, it's manifestly, if you exchange ST, TU, it's manifestly invariant. But in this formula, it's not, it's formulated within some channel. Say we take energy and we take angle, and so there is no obvious crossing. And then I told you without showing, and I'm afraid I don't have time to derive this, but it's really just complex analysis, and in the notes that I uploaded, you can go over it. It's really simple, that it's convenient to reformulate this elastic unitarity in terms of this Mandelstam equation. And this Mandelstam equation, it's a statement, it's also a statement of elastic unitarity, so it's formulated in this elastic strip. It uses analyticity in this second variable t to derive it. And it expresses the double spectral density as the integral of some kernel. In fact, this kernel is positive, times the discontinuity. So this little label t, I use it as a discontinuity in t. So again, if you have a cut, you go above, you go below, you take the difference. This is a disk. So this equation is called Mandelstam equation, and you can ask, okay, well, you did it, you derive this equation. It has the same physics, more or less. Why is it useful? And it's a bit useful because if you now look another question that we asked, we saw that there are these non-analyticities and they have some structure. And I told you that, say, this guy, it associated to normal threshold at 4n square, you produce 2 particles. At 16n square, you produce 4 particles, etc. But it's perhaps not obvious, but a true fact that this double spectral density has non-trivial support along non-trivial curves, and this is called Landau curves. And so this is the picture. And here there is a nice split between multi-particle physics and elastic physics. So all these diagrams, and in fact, I forgot to tell you that one thing is that you all know that perturbation theory diverges, the number of diagram diverges factorial, it does not converge. Most of the graphs which produce, in fact, the graphs which are responsible for this divergence, this is a multi-particle physics graph. They diverge because there are so many channels are opening, and to correctly capture them, you need many graphs. And so all this multi-particle physics, all the complexity is sitting here. And the gluing along the 2 cuts is sitting here. And these curves, this is what these 2 curves, these are called Landau curves. And this is where the support of rho develops. So say, if you go here, rho is 0. And if you cross the cut, it becomes non-zero. So, and now, even though this picture, if you wish, this picture you can derive from just this 3-loop calculation, this picture is also non-perturbative. If you take the full amplitude for scattering of pions, we believe that this is the right picture. Now, the end of the lecture 1, I stated that why is scattering in high dimensions complicated? So we know in 2 dimensions there are integrable S matrices, and the basic answer is that it's because in 2 dimensions you can live without particle productions. So why? And as you start producing particles, you run into this MP physics, which you have to deal with, say something about it, and this is what we need to learn how to do. And one way to nicely to express this fact is the so-called Axe theorem, which says that scattering implies production in space-time dimension larger than 2. So I thought I will now use this structure that we revealed to prove this theorem quickly. How does it go? Yep.
So you mentioned that, for example, for pions, you expect something like this to hold.
Yeah.
But imagine you have something like the Cayley parameterization, where you can have any even point interactions, right? Wouldn't you expect to have even more, channels with even more particle production, like 6, 8, so on?
Oh yeah, sorry, they're all there. They're all there. So, but the thing is that there are Landau curves, for example. You see these Landau curves, it asymptotes to 4 in T channel, and it's asymptote to 16 in the S channel. And this is, you can see from the graphs that it generates, it's 4 particles in S, in 2 particles in 2. So if you have a graph with, say, 6 particles in S, 2 particles in T, there will be Landau curves like this, etc. So there are many Landau curves, but all the Landau curves which enter this strip, they have a 2-particle cut. All the Landau curves that enter the strip, they also have 2-particle cut. Landau curves, which are here, we do not know much about them. They're very complicated. As I told you, there are accumulation points. It's a very interesting problem to understand this. And in fact, yeah, to find this Landau curves, people also solve this Landau equations, but it's the same thing. So yeah, all these Landau curves are there, and the elastic strips, they are picked exactly by this property. Remember on the first slide, there was this set of graphs generated by two-particle gluing. So they will be producing Landau curves that live here and here. And these guys, which are more like this, they will be pushed higher in the complex plane. So it's a little bit like an onion. We believe the structure here is a bit of an onion. If you take a graph and you say cut it in like this, and you have 8 particles here and 8 particles here, this guy will be further in the complex plane. So they are all arranged hierarchically according to the energy.
I have a follow-up question.
Yeah.
So is the Mandelstam representation the exact answer then? Or, I mean, I feel like you would need more corrections with more poles.
Okay, so let's go back here. It's an exact answer it's an exact answer in the sense that, you know, these two functions can be very complicated and encode very complicated physics. For example, all these Landau curves, they encoded here. Multi-particle threshold can be encoded here. You can also have things on top of this, which is you could have bound states. Let's say you have your threshold 4n square and you add an extra pole, and this is a bound state. And this could be before. So here I assume that you know theory well enough that you know the spectrum of light particles, and you say consider scattering of the lightest particle, and there are no bound states, which is say true for pions. And so then you do not have any singularities. So from this point of view, it is an exact answer, but in a somewhat maybe not very satisfying way, because it's an exact answer that implements maximal analyticity and it's crossing and polynomial boundedness, but we do not know all the physics is sitting here. I hope it answers. Okay. So let's try to prove the Axe theorem and hopefully learn something from that. How does it go? Again, here the statement is that if you have scattering, you must have production. Why is that? Well, let's assume that there is no production. Let's assume that there is no production and the scattering is purely elastic. It means that this equation now holds not just in the strip, but for any energy, right? Because there is no production, so this is trivially true, so we can use this equation for any energy. Which means that here I draw this dashed line, but I don't have to draw it anymore, and this Landau curve controls correctly the double spectrum density for any energies. And in particular, I told you that below this Landau curve, spectral density should be 0. It means that here, everywhere, spectral density is now 0. And here, this is no production. This is the first step. Well, if you have the picture like that, then the second step is we use crossing. And this is why I switched from, I told you unitarity picks a channel, but spectral density is crossing symmetric. And so this picture should be invariant under the flip of S and T channels, and it is. And if I told you that unitarity says that spectral density is 0 here, it has to be 0 here as well. So therefore, we conclude that in this region, in this elastic region where we expect this, say, this density to be generated, in fact, it's not. It is 0. And then the third step, which leads to a contradiction, is the following, that you can argue, in fact, that if you have scattering, it has to be strictly positive. And this result is known as a Martin-Maul region, Martin-Maul region. And this is a statement that exactly someone asked me about higher threshold. It's a statement that this elastic spectral density, if there is scattering, must be strictly positive in this region between two Landau curves. One is due to our familiar graph and one with a third one. So how do you prove something like that? You just take the Mandelstam equation you plug here partial wave expansion in this formula, says T of T. You just plug the partial wave expansion, which is this formula. And then you simply use the fact that the imaginary part of f is positive and this series converges in some region. And then you find that the kernel is positive, everything is positive. This guy has to be positive if scattering is non-zero, which means is f of j is non-zero. That is what it means that there is scattering. And you see, so we got two different conclusions. From no production, we concluded that rho is zero. No production led to rho equals zero, whereas scattering led to rho positive. So this is a contradiction, and therefore scattering implies production in d larger than 2. You can ask, where did I use d larger than 2? Well, it's in fact that we have two variables. We have transferred momentum and energy. In 2 dimensions, the amplitude is just a function of one variable, which again physically means that you cannot separate wave packets in the transverse space. You just scatter on the line. So this is where d larger than 2 played a role. So this is why scattering amplitudes in d larger than 2 are complicated. But maybe there are questions. Okay. Now, whenever we prove something like that, the next question is how much production do we have? I told you that scattering implies production, but what's the minimal amount of production? And this is a really interesting question, and this is what I will now start. I start here, and I will try to go from here. Now, there is a question, or?
Sorry, in this proof, why did you need step 2? Because like if you just have step 1, there's no production below, and then you use
Perfect. So let's say I do not have, thank you. Crossing was essential because let's say I just told you that spectral density is 0 here where I dashed it. And then I told you that, well, scattering implies that rho is positive here. There is no contradiction, right? Rho is positive here. It is 0 below this curve. It is all fine. It is the crossing that says that something which is non-zero here and 0 below this curve, they should be equal. This was a crossing step.
Thank you.
So yeah, it's interesting because we use unitarity and crossing.
I have a question.
Yeah.
If I just look at this proof, what's the difference of d equals to 2?
Okay.
The theorem applies to d equals to 2, but the whole argument doesn't mention anything about dimension. Okay, sorry. I thought that I explained it, but it seems like it's not clear. So let me just write it explicitly. D equals 2. In this case, just t equals 0 kinematically. You know, what is S and T? You have two particles. They come. You have two particles. They come and they go. So in 2 dimensions, they cannot. The scattering is on the line in 2 dimensions, which means that it's always forward. And so T is equal to 0. Therefore, this whole argument, everything I'm talking here is just does not exist in 2 dimensions. From the very first line, the amplitude is a function of one variable. In 2 dimensions, it's just a function of S. There is no T. So, therefore, you cannot apply this argument. And again, the pictures that I like to have in mind is that when you have a scattering experiment, you have wave packet, you can separate them. You cannot separate them in 2 dimensions. They are on the line. It's a head-on collision. Is it clear? I can try to find another way to explain it if it's not clear. So,
It sounds like it's clear.
okay.
When I give to the way to the students, I might suggest you hold on to it until Sasha's done with the question, just so you can tell him if that's okay or not.
Yeah, as we say, it's certain silence is an enthusiastic agreement. Now let's ask this question: what is the minimal amount of production? And this will be an interesting question because, well, as you will see, what does this picture tell us? Well, this picture tells us that in the full theory, I can write a double spectral density as a sum of three terms: rho L as T, rho L TS, plus rho MP. And physics of this split is, again, this picture. And as I told you that the basic point is that this, if we, in some sense, if we want to fix all, in this equation, different physical theories will have, if you wish, could have different multi-particle physics. And so the space of amplitudes is parameterized by this multi-particle physics. So if we want to close a set of our equations, in a sense, we can think of this as a source. And think that we have multi-particle physics as a source, if you wish, in the language of my first slide, all these complicated graphs, which are not two-particle reducible, I pack into this very complicated blob, which I can call then an MP blob. And it will drive these iterations of unitarity. In other words, if you have a given theory, so Feynman diagrams, they're smart, and so they implement all unitarity at once, not just 2 to 2, but they also know about 2 to 4 unitarity. So they know that if you want a 2 to 4 unitarity, you have to add this graph. But if you want to do some non-perturbative calculations, we cannot deal with these graphs. We need to do something else. And one way we can think about it is, well, let's just parameterize all this multi-particle physics by this unknown function and try to find a way to explore the space of theories or to do something with this function. And then if I consider this source as being fixed or being completely free, I might be able to make progress. And I would say that since the beginning of the subject, there were roughly 4 solutions or 4 approaches, 4 ideas suggested how to deal with it. Yeah.
Can I ask a question? So why is rho elastic depend on 2 Mandelstam? Isn't it just so in your Mandelstam representation, it just depends on 1 Mandelstam, right? The
rho elastic is a part of this guy.
Oh, okay.
So rho elastic is a part of the double spectral density, which sits here. So S is between 4 and 16, but T is arbitrary.
Thanks.
So that's why it is an elastic strip. But you're right. There is also this guy, and I'm sort of sweeping it under the rug, that this guy is also there, and it also satisfies elastic unitarity. And physically, what it does, it corresponds in this equation to dealing with J equals 0. So in principle, you should separately, let me not go into that, but you should separately treat the equation when J equals 0. And this will lead to an extra equation, which is not a Mandelstam equation, but just an equation for rho in this elastic strip. But it's important, yes, that here is that S is between 4 and 16, and T is actually arbitrary. It is a little bit, in fact, it's a little bit fascinating. You might think that you start with something which you thought is low energy. S is between 4 and 16, but I'm telling you that this equation secretly controls some property of the amplitude at arbitrarily high energies. So T is arbitrarily large. And this is this magic of analyticity. And
You can prove theorems about properties of high energy scattering based on this seemingly low energy equation. So yes, the answer is it's elastic strip. Okay, we have to deal with this MP term. So how do we deal with that? Well, let me start with the historically first way, which is already non-trivial, and ask, well, maybe we, even before we go into this subject, how do we know that the set of these equations that describe unitarity, where someone gave you this multi-particle physics piece, and you have to solve unitarity, you have to solve the Mandelstam equation, you then have to impose crossing by using this equation. What do we know about space of solutions of this amplitudes of these equations? And there is a nice result by Atkinson from, again, 1968, as I told you. He proved a theorem which roughly you can say that if if rho MP is small, the solution is unique. There is an important technical detail here. He considered the setup, which is what is without the subtractions, where you set this to 0, you don't have this extra term. So everything is just, in his setup, there is only rho. So think of this regime where you just have one function. And then he showed that if you drive scattering by production, so this is some kind of production, and we try to find scattering, he shows that if this rho MP is small, then the solution is unique. And the beauty of this result is that you have this equation which is nonlinear. You have dispersion, this dispersive Mandelstam representation. It's not obvious at all. But the beauty of his result is that he thought.
Sorry, I had a question.
Please.
Yeah. Is that a typo that we did not impose crossing for rho MP, or does that part not have to?
Oh no, sorry, we do. It is so here. This rho MP will be crossing symmetric. Yes, rho MP is crossing symmetric, and it will in physical theories again. Look at this graph. It's invariant under if you rotate it by 90 degrees, so it's exactly a crossing symmetric thing. So let me write it. Let me write it. So when you drive your system by production, when you turn on the source, you choose the source to be crossing symmetric. And then you start solving these equations, and you get something, or maybe you don't get something. But what he did, he chose the source to be small in some norm. So he has to choose the functional space, which turn out the space, which is, you want a space of function which is preserved by plugging them in the dispersion relations. And it turns out that the space is a space of Hölder continuous functions. And then he identified the norm in the space, so it was some Banach space. And then he showed that unitarity is a contracting map. Which is maybe familiar from you when you, if you take a cup of coffee and you stir it, the surface of the coffee is mapped to itself. And in general result is that when you have such mappings, there is a fixed point on the map, because you cannot move everything if it's a continuous map and a finite norm. And so if it's contracting, and moreover, it means that the size of this region collapses on the iterations. And so he started with some source, and he started iterating this equation. You start with the source, you compute the rho, you compute T from the dispersion relations, then you can plug them in the Mandelstam, you get rho L, you plug it back here, it's a step 2. Now you get a new raw. And now you go back, you go to the amplitude, you go to the Mandelstam representation, you recompute row L, and you get these iterations. And this is exactly the same spirit as we did with Feynman diagrams type of iterations. And he showed that unitarity is a contracting map, therefore there is unique fixed point and the solution exists. And that's more or less everything that was known until these equations. And
Sorry, Sasha?
Yeah.
So how applicable is this assumption that the multiparticle density is small?
Very good. Let's do this is the next step. Let me just it's a very good question, and unfortunately I will not give you a good answer probably, but let me continue practically. So let's try to just see what is the space of these solutions when rho MP equals to 0. Let's just start with something simple. And what does it mean physically? It means that we are considering a set of Feynman graphs where we continue this gluing forever. We just focus on these graphs where we do them gluing by 2-particle cut, and we consider all planar graphs which are generated like this. Of course, if you try to compute them, it's a hopeless exercise, but the claim is that the equations that I present you, when you set rho MP, this is precisely what you're doing. And when rho MP equal to 0, because you throw away all these complicated graphs. In some sense, you can think this is a solvable, some kind of solvable model, or something the analog of integrable model in some sense, which in the past, when in the old days, and this is what people call this strip approximation, and the word strip here refers to this elastic strip. So we approximate our raw by this things, and we throw away any empty physics. And I believe people thought that, well, maybe we are lucky, and actually QCD is of this type. And then let's say we can solve first rho MP small or 0, and then we turn it to small perturbations, and so we get some kind of a non-perturbative bootstrap perturbation theory, where at every step you have non-perturbative amplitudes, and you correct this rho MP. But the short answer, I don't think we know which theories are of this type. I think we know for sure that QCD is not of this type, and that's why this in the 60s this is a sort of the one thing people tried, and it didn't really work, and well, they couldn't even find the solutions. But let me now yeah. I hope it answered partially the question, but we will continue discussing this. Now, let me ask, what do we know? Let's set rho MP to 0. Now, in principle, I can try to solve these equations and get the amplitude as a function of lambda and S and T. These functions, they perhaps exist, and they correspond to resummation of these graphs, and they are perhaps as close or close. One attempt we can get to having something like integrable theory in high dimensions. So let me just not worry yet about what it corresponds to physically, but try to compute this function. And this is an interesting problem, because now we have a non-perturbative set of equations, which is a Mandelstam representation and Mandelstam equation, and you can just go and solve them. And in fact, the solution was only constructed in this year, so it's 60 years later, and it's interesting, and it does exist. And so let me just tell you how it was done. And what are the properties of the of these amplitudes? Just very briefly. One interesting aspect of this problem is that you see it's integral. You have this integral representation. You have nonlinear equations. And in general, the simple method of Atkinson that it's a contracting map does not work. If you increase the coupling here, in the problem with lambda, if you increase the coupling, there is no convergence, so you have to do something else. And long story short, well, maybe you will come up with a better way. But one useful way that we found for this problem is that we parameterize the amplitude by a neural network. So you take your Mandelstam, say S and T. Let me just say with one variable, introduce X, which is 4m squared divided by S between 1 and 0. This is where my spectral density leaves. And then I feed it in. And it turns out that to solve this problem, somehow you need a nice architecture of the neural network. So you introduce separate variable, separate subnetwork for the high energy limit. So it's well, let me just call it Regin network. So some set of layers which take log x, and this is related physically to the fact that when you start solving this problem or physical problem, you sometimes you get large logarithms, which you can resum using our G equation. And so if in particular in this 5-4 theory, you get large logs. And when you're trying to solve this problem numerically, you immediately run into that. And so neural network, it helps if you create a sub-brain which learns the Regin limit, and then you create a subnetwork which learns, say, intermediate energies. And then the nice thing about this neural network architecture, which is just an approximator of a function, in this case an amplitude, you can seamlessly then put some intertwining layers, and the outcome you get your spectral density. And then, now there are these powerful optimizers, and you can just do this exercise for this problem. And the result is that indeed you find that this function T lambda ST, there is a question. Or maybe not. Well, you will interrupt me. The result is that this function exists, and you can construct it, say, for lambda between, say, 0 and some critical value, which we got something like 70 pi. Some physics is here is that why is it positive? This is exactly the sign I don't know if you remember, I started my lecture and was telling you 5 to the 4th. And for one of the signs, you have Landau 0, and for other sign, you have asymptotic freedom. And this is precisely the sign for which you have asymptotic freedom. And if you try to do it for Landau 0, you just do not get a convergence. So you kind of see the Landau 0 by not finding the solution here. But asymptotic freedom is perfect. Then you see that there is some maximal coupling beyond which you just do not find a solution. And otherwise, for these functions that you get, and they're parameterized just by one coupling in this procedure, they satisfy all the non-perturbative properties of the amplitude. They satisfy crossing, they satisfy elastic and inelastic unitarity. And if you look at the partial waves and the absolute, remember that S of j equals 1 means no production. And Sj less than 1 means production. The probability to stay 2 to 2 is less than 1. It means that some probability is taken to 2 to 4, etc. And here, basically, as predicted by Ox, this function is cannot be elastic. And so indeed we find that if you plot this Sj as a function of, say, energy, let me use this x, 4 squared divided by s, from 1 to 0. You find that, well, as expected, these things, they start elastic, and then they develop some production, and then they go to 0. So asymptotically, scattering becomes transparent, but all these partial waves they developed, which we can call this Ax bump, which is precisely related to this fact that you know, if you have this graph, which is a 2-particle cut, by crossing you will have this graph, which is 2 to 4, which is a production. And indeed, you see exactly that this is what happens. You also see that the amplitude is non-perturbative. For example, you can ask what is the Regge limit of this amplitude, which you can also compute. And you see that the Regge limit, and sorry, I don't think I ever defined, at least in this set of lectures, say Regge limit is S goes to infinity, so high energy, T fixed, small fixed transfer momentum. You find that this function goes, say, some constant, and then there is an expansion in the inverse powers of a logarithm, square root log of S. Of course, this is not something you get from Feynman graphs, because now it comes from a resummation, which is done by solving this equation, and then you get whatever log 3/2, etc. Anyhow, this is just to say that to my knowledge, these are the only known sort of explicitly computable functions which behave like non-perturbative amplitudes at all energies, and we can understand them at fixed angle, high energy limit. We know what they microscopically mean. But coming back to the question some of you that asked me this, of course, it's not yet satisfactory because well, I started by this conditions. That's how I define the function. But I think the answer I can give is that we believe, it hasn't been proven, but this kind of amplitudes, they are close in some to be properly understood way, they're close to phi to the 4th, perhaps in 3 dimensions. At least physically, it seems like this is what it is. But let's say if this is even correct, it would mean that if we take a weakly coupled phi to the 4th, then it should be inside. There should be a way to check that and to see that it's small, but this is not understood. So far, this is the state, I would say, state of the art. And in some of these logs, in fact, they have been predicted and computed using the Regge theory, but let me not go into that. Instead, yeah, if there are no questions here, what I try to describe to you that there is a solvable model which is defined by setting this rho MP to 0, which means you throw away all these graphs which are not generated through 2-particle gluing. And this function you can compute, it exists, it solves the equation, it satisfies all the unitarity properties, it exhibits production as expected, and it exhibits some interesting Regge limit, etc. But we don't. Yeah.
Did you say this is supposed to be close to the phi to the 4th at weak coupling or at any coupling?
Okay, well, in 4 dimensions, first of all, in 4 dimensions, you can, of course, complain there is no phi to the 4th, but then let's go to, say, d equals 3, and there, I don't know, yeah, it's a good question. I would say it's weak for sure, but the question is then, as you start increasing the coupling, how long does it How long does it hold? Because at weak coupling, this MP graphs, they seem to be suppressed. They do not have a mechanism in them to get enhanced. For example, in QCD, or maybe I'll comment about it later, raw MP is very important. And effectively, we know it from experiments. The cross sections are growing. You can see that this should be related to this raw MP. But in phi to the 4, it seems like the amplitude decays with energy, and in some sense, this high MP region does decouple, but exactly how and at which coupling, etc., it's not understood. Yeah, I don't. So honest answer is that I don't know.
Thank you.
Okay. Now I want to use this example, which is fully, if you wish, fully understood, I hope, in the sense that you have a definition in terms of Feynman graphs. You have yeah.
Sorry to interrupt. I just wanted to ask, is there any way you can carry through this kind of analysis in like dim reg around D equals 2?
Around equals D equals 2.
Yeah, so you move just away from where you have these kind of trivial exact results. You like get any interesting analysis in epsilon?
I don't know. Yeah, it's interesting. It's a little bit. I find it. Yeah, I don't know what's the right way to think about it, because when D equals 2, there is a dramatic reduction of the amplitude is structurally different because T is set to 0. On the other hand, I guess in dim reg you have S and T, but maybe you're saying that close to 2 there is some magic that or some simplicities that emerges. Yeah, interesting question. I don't know.
Thanks.
Okay. And let me now come back to the question that I asked sometime earlier, which was, what is the minimal amount of production? Because from what I said, it's completely not obvious. I said, well, we set rho MP to 0. It seems like where multi-particle physics is small and we get production. But in fact, from what I told you, it's not obvious that rho MP equals 0 is a optimal solution to this problem if you want to reduce the production. And so let me try to add to this problem the following target. When I train this neural network, let me ask it on top the target, let's say find rho MP such that, say, there is no production in the spin 0 partial wave and there is no production in spin 2 partial wave for any energy. Can you do it? And the answer is yes. In fact, it can do it. And so you will learn, you find some rho MP, which acquires some complicated structure. They start oscillating in this region in some way, such that they precisely cancel the when you use this rho to compute some particle production, they cancel whatever the production was generated by this argument. And so this has a tuned amplitudes, but they exist. And well, I said S2, but why not 4? And yes, indeed, you can add, and it seems that for any j, you can arrange for any j less than some j0, you can find these amplitudes with this rho MP tuned to some crazy thing where the production is completely cancelled. And this immediately, yes, this tells you that the moral of this, okay, the ox argument, it was formal and it was very nice, but probably many of you have never heard about it because, well, to have a physical implication, you don't just want to say that there is particle production, you want to say how much. And this was never done. And here we're just explicitly constructing amplitudes where by hand we can impose no production at finite energy and at some finite spin. And therefore, the statement of the Sachs theorem, unless we learn something about this
unless we add some extra physical input about this raw MP and just don't let it fluctuate wildly, we see that it can screen all this production at finite speed. So the lesson which I would like to draw is that here is that you see that, say, for some questions we use this raw MP to close the set of equations, and then we took something which, let's say, something simple, and we get sum of graphs which has a physical interpretation. But then if you ask a formal question where you say, I don't care where this raw MP is coming from, I just take some random function and I want to reduce particle production as much as I can. The answer is that you will do it. There is no principle in what I told you that will prohibit that. And from this point of view, it seems to be that if we want to understand the questions like particle production, we need to understand, say, something about this multi-particle physics a bit better, some input. Maybe we need to extend the equations or add some extra assumption. For example, if you add the assumption this raw MP cannot be very big in some region, you see that the screening disappears. But unless we provide some extra input, say this result by X and this physical expectations that your theory will producing, we see that it's just not there. And this is perhaps a surprising result. But this is what comes out of this program. And let me remind you again that in this matrix Bootstrap, all the work essentially is done for 2-to-2 scattering. And so this raw MP is always treated in some semi-agnostic way. And this is, okay, let me ask, sorry, is it maybe clear? Is it clear what I was, what I was explaining here is that if you allow yourself for this raw MP to be arbitrary source, you can explicitly see how you take the solutions and screen this X argument. And in a way, there is this conundrum. I gave you one argument that the production must be there. It was a bit formal. It does not tell you how much. And I gave you another argument, perhaps more physical, that in any finite number of partial waves, you can screen it. This does not sound satisfactory, perhaps, to you. So where's the truth? What exactly is the statement? It doesn't sound perhaps satisfactory to me also, but that's where we are. So this is one. Yeah.
You were allowing that S2 is greater than 1, right? So not imposing unitarity. What happens?
Sorry. Here, so the statement is here with this raw MP equal to 0, I just found that it's less or equal than 1. Now, when I allow myself, when I say, do this raw MP, I do impose that all the S of J are less than 1. I do impose that. So the amplitudes you get, they satisfy all the usual unitarity, but in certain partial waves, you can remove all the production. So you see that raw MP starts developing some positive and negative parts, and they develop in exactly such a way to insert in partial wave to completely screen the production. But the amplitude is still completely unitary.
Okay.
To the extent we can control it.
Sorry, another question.
Mm-hmm.
So are you saying that you can get it to set any number of SJs equal to 1, or can you tell it, for example, just give me the S2 equals to 1, or independently, you could just give me S4 equals to 1, but you can't say, for example, give me S0, S2, S5, S7 equal to 1.
No, you can impose all kinds of game. It seems like, okay, I'm now telling you some numerical results of numerical experimentations, and you simply see that you have as your source a function of 2 variables, which is quite a lot, and then you're asking a functional equation in one variable. And maybe intuitively it's clear that you can, and the two are related by some kind of moment integral. And what happens is that it's just this function rho MP, it arranges itself in a way that it contributes to certain moments precisely in a way to cancel all the production. And then, well, you can ask, okay, what happens as you try to take the limit? Let's say you try to impose it in all J's. Jesus, there is no production. We have to run into some contradiction with this AX argument. But presumably what happens is this rho MP, it becomes infinite. Or it becomes some nasty distribution. But what precise statement is, I don't think it's known. So this is where we are. On one hand, there is this formal argument, there is production. On the other hand, you can construct amplitudes where for short or finite number of partial waves, you can remove it. You can still have production in higher partial waves, but then, if you're allowed to push it higher and higher, it becomes a bit of a formal statement. Because, as a physicist, you measure finite energies and finite partial waves. And if I can remove production from there, so for you, effectively, there is no production. And I think it's a bit of an open problem. What precisely is the property of, say, rho MP, or how do we exactly remove the situations? And I wanted to explain it in that way because what I will tell you next, we will be seeing all the time amplitudes without any particle production. And at first, maybe if you might be puzzled, why does it make sense? You're used to particle production and to all these graphs, but first I wanted to explain to you that we start with the problem of 2 to 2. We run into this multi-particle conundrum that if we want to close a system of equations, we have to include all the amplitudes. This is too hard. So we go to 2 to 2. Effectively, then we have some multi-particle thing we don't know. And then if you don't know anything about it, then it turns out that many things are possible. And in particular, you can sort of effectively evade this AX argument in the sense that you can screen the production. And again, what is the expectation? Well, the expectation is that if you take this rho MP that screen the production and you try to cut it and check, say, the unitarity 2 to 4, something like this, you probably will find some nonsense. But because you're not including these equations into your system, there is no way to tell. And yeah, just to be clear, when I said there are 4 solutions, how to do with rho MP, this was one of the solutions in the, say, old days, to assume that it's small and to develop perturbation theory in it. So, as we discussed, it's not really maybe a good solution because we do not know why is it true, and in fact, in many theories, it's just not true. And so now I will proceed. I want to proceed, start discussing the second solution, because we have to say something. What do we do with this multi-particle physics? And the solution number 2, which is very, in a sense, much more recent, is just the following: be completely agnostic. Agnostic about rho MP. So let it do whatever it wants, and maximize or minimize physical observables. This will be the second solution. It is a much better, perhaps. It is a much better solution because now the questions, well, why did you assume rho MP is small or large or whatever? It does not arise because if we are completely agnostic about rho MP, we know that all the physical theories are inside or within this range. Any questions?
No questions, but I'll just let you know you have about 10 minutes.
Yes. So let me start describing this basic idea of solution number 2.
And well, I told you maximize, minimize physical observables. Let's first pick an observable. Well, one nice observable is let's take the amplitude and expand it at low energies. Let's expand it around the point, crossing symmetric point, S equal S0, T equal T0. Then, as we discussed, the first term is lambda. That's how it was defined. It's a value of the amplitude at the crossing symmetric point. The next term is just the Taylor coefficient. You can take S minus S0 square plus T minus T0 square plus U minus U0 square plus dot dot dot. And you might ask why there is no linear term. Well, there is no linear term because kinematically S plus T plus U equal to 4m squared. Now, for any amplitude that you compute, you expand it at low energies, and it will have some numbers here. So there are two numbers, this and this, and we can choose them as our physical observables. So this would be done. So let's try to maximize and minimize lambda and C2. This is the target. Now, we want to, how do we do that? If we are completely agnostic about rho and P, well, we can run in principle the same max-min procedure as I described to you. You just ask to construct an amplitude with such rho and P's at max and min as these things are minimized. But people actually found a much, much simpler and efficient way to do that. And the way is, in a sense, you just forget about everything you know from this is everything you learn from Feynman perturbation theory and this fine structure of unitarity, and you just write a very flexible ansatz for your function. You write this, you want to construct a big set of functions, and one convenient way is you do some kind of Taylor series in 3 variables, say rho S A, rho T B, rho U C. And this rho of S is simply a map of a cut plane into the unit disk. So you can define it as a, say, 4m squared minus S0 minus 4m squared minus S, 4m squared minus S0 plus 4m squared minus S. And you can check that if you start with a cut plane, where you have the cut at 4m squared, it just maps it into a unit disk, where this is a rho of crossing symmetric point, which is 4m squared over 3, it's not. So one, it's a map of a 2-particle cut. And then say, if you go above the cut to infinity, it's just maps to the boundary of the disk here. And now you truncate the series. You take finite n here. Effectively, you develop Taylor series, and you see that this ansatz, if you take this alpha ABC to be symmetric, it satisfies crossing symmetry. You flip ST or TU or SU, that's completely symmetric if these numbers are symmetric. It's linear in these alphas. And by construction, it has maximal analyticity. So it has maximal analyticity. It is of, if you wish, of this Mandelstam representation type. And what is the picture? Well, you expect that if you take in practice, you always take this n to be finite.
you expect that you approximate your amplitude in some region relatively well, let's say. And as you take n to infinity, you hope to recover the amplitude. Now, we impose crossing, we impose analyticity. So analyticity is done because it has the right analyticity. Crossing is done because we can just choose alpha ABC, alpha BAC, etc. So the only thing that is left is unitarity that we need to impose. And here again, let's be just very, very well, do it in a simple way. We just impose Sj less or equal than 1. So we forget about elastic unitarity. We don't have any Landau curves. Here, if you compute the double spectral density, it starts right away after 4. It's not 0 there where it should be 0. But let's just not worry about that and hope that for some observables, say for certain observables, and say double spectral density is not one of them, it is a good approximation. Let's just hope. Reasonable n. Yeah, maybe let me just comment that this is.
Hi, Sasha. I
Yeah.
have a question.
Please.
Also, you choose the n is a finite number, right? So you said you just consider, or maybe we assume this is a well approximation of this amplitude. Are there any? Okay, I want to know are there any good example we can see this is really a good good ansatz or good basis?
No, not that I think that you can also modify the ansatz, make it more flexible. And it seems like for some questions, in particular for low energy physics, you can make it flexible enough that it can approximate the amplitude in the physical region relatively well. So I don't think we have an example of the amplitude which say we fully know and we can check in all regions, but let's say we consider scattering of pions, and people use this sort of ansatz and their more complicated variations to derive certain interesting results about them. And it seems like it can capture many features of the amplitude. But I think the way you can think about it, think of this as an approximation for some questions. If you ask too many questions, it will break down. But for example, let's say I want to minimize, my target is to understand the space of these amplitudes and construct some interesting examples. For this purpose, it seems like it's a very useful way to proceed. So I'm taking a sort of practical approach. I think it has proven to be very fruitful. So that's why but in principle, if you want, let me give you maybe another argument. Let's say I take a fancier approach. Instead of doing this Taylor series, I go back and I take a neural network. I introduce all the structure. I introduce Landau curves. In the examples that we know, and for the questions that we know like this, the answers are the same. And the intuition is that it seems like for this low energy type questions, it's actually not so important. And yeah. And now I think my time is up. So next time I will just tell you what the answer is, and proceed with this solution and slowly maybe other solutions. That's it. Thank you.
Maybe one last question before we break for the day? Here we go.
All right, thanks for the talks. So just to understand dropping the linear term here, so did you just reabsorb it into what you call lambda?
Absolutely, yes.
Okay, great.
Maybe I have time for one. Do you have a question?
Yeah.
Yeah, just one more quick question.
So in the expression that you wrote with the alpha ABC and rho to the A, is it possible to constrain this using how T of S comma T grows as S goes to infinity in the complex plane, and does that polynomial place any constraints?
If I understood the question correctly, you're asking what is the behavior of this at high energy limit of this ansatz?
Yeah.
Yeah, it always goes to 1. So all these functions at high energies, they always go to 1, which is of course not what you expect from the AMPAT yet. But I think maybe one way to think about this ansatz is that when you're doing the effective field theory calculations, you describe your function with some UV cutoff, and then eventually you hope maybe to remove the UV cutoff when you become infinitely powerful. I think that this ansatz, you should think about this, that it works for given n, for a given n, it works well with S less some S0 and the spin also less than some J max. It is kind of an EFT way to parameterize an observable. And roughly what you expect is that, let's say you want to see an amplitude which grows at high energies. When you start parameterizing it with this ansatz, you will see something which starts growing, and then effectively you hit your cutoff, you don't trust this function anymore, it goes to 1. And so then effectively, yes, the formula, if you take the S to infinity, the function goes to 1, but this is not what we will be looking at. We will be looking at some interesting behavior at low energy and then slowly removing the cutoff and see what emerges. So here the idea is think of this as some kind of EFT for an observable expansion. And as you remove n, the range of this observable gets bigger. That's, I think, the way people use it.
Thank you.
All right, let's thank Sasha again. And just a reminder, after the first lecture tomorrow, we will do the TASI photo during the break. See you then. Have a great day.